Hello everyone. Today I will focus on one of the most fundamental concepts in real analysis, real sequences and their convergence. This is the outline of my presentation. Sequences appear everywhere in mathematics. For example, it appears in approximations, iterative methods, numerical computations and limits of functions. Here we will discuss what sequences are, how they behave and how to determine whether they converge. We will give special emphasis on the uniqueness of limits and the fundamental theorems that describe convergence. Understanding convergence is essential for understanding advanced topics in advanced analysis. Before going to the details, we first introduce what is a sequence. A sequence is a list of numbers arranged in a definite order. Thus, an ordered list of real numbers forms a sequence of real numbers. So, in a sequence, there is a first element, a second element, a third element, and so on. Ordering of sequence is determined by the ordering of the natural numbers, and the ordering plays a crucial role when we study convergence, monotonicity, and limits. Formally, a sequence is a function whose domain is the set of positive integers. When we say A is a sequence of real numbers, basically A is a mapping from n to R. Here A suffix n means A of n. These are some common examples of sequences. Now let us discuss the concept of a bounded sequence. Let n be a given sequence. Then n is said to be bounded above if there exists a real number g such that n is less than or equal to g, and the sequence an is said to bounded below if there exists g1 such that g1 is less than or equal to n for all n. A sequence is said to be bounded if it is bounded above and it is bounded below. That is, there exist real numbers g1 and g such that g1 less than or equal to n less than or equal to c for all n greater than or equal to 1. Equivalently, a sequence n is bounded if there exists a real number m greater than 0 such that mod of n less than or equal to m for all. Here m is the maximum of mod g1 and mod g. Some example of bounded sequence are sin n 1 by n, 5 plus 1 by 5 plus minus 1 to the power n. For sin n, m is equal to 1. For 5 plus minus 1 to the power n, m is equal to 6. We now come to the central concept in the study of sequence, namely convergence. Let an be a given sequence and L is a real number. Then an is said to be converged to L if for epsilon greater than 0 there is a natural number n1 such that mod of n minus n less than epsilon for all n greater than equal to n1. This definition is the backbone of real analysis. The above definition says that if n is a convergent sequence, then term of the sequence gets arbitrarily close to n as n becomes arbitrarily close to L as n becomes large. Thus, the convergence of real sequence n is the study of behavior of the real sequence for large values of n. Beyond some fixed index n, all terms of the sequence lie in the small interval L minus epsilon, L plus epsilon. Here, n1 depends on epsilon. And we write limit n tends to infinity an equal to L and or an tends to L as n tends to infinity. L is called the limit of the sequence. If no such L exists, the sequence is said to diverge. Now we shall prove an useful result, the uniqueness of limit. This result says that if a sequence xn converges, then the limit is unique. Let n tends to L and let xn tends to L and xn tends to m and L not equal to m. Since L not equal to m, mod of L minus m by 3 is greater than, take epsilon is equal to mod of L minus m by 3. Then for epsilon greater than 0, we can find a natural number n1 such that mod of xn minus L less than epsilon. At the same time, mod of xn minus m less than epsilon for all n greater than equal to n1. Then mod of L minus m less than 2 epsilon, putting the value of epsilon, we get mod of L minus m less than 2 by 3 mod of L minus m. Since a mod of L minus m is a positive quantity, this is a contradiction, and this proves that L is equal to M. Thus, a convergence sequence cannot converge to different limit. Now, if we consider a equal to 1 by n, then limit n tends to infinity 1 by n equal to 0. Because for epsilon greater than 0, we can choose n1 greater than 1 minus 1 by epsilon. This choice is guaranteed by Archimedes property of real number. Then for n greater than n1, mod of 1 minus n minus 0 is less than 1 by n1 less than epsilon. Thus, for each epsilon, we can choose a natural number n1 such that the definition holds. Therefore, limit n tends to infinity 1 by n equal to 0. For the constant sequence n equal to c, mod of n minus c is equal to 0 less than epsilon for every natural number n1. Therefore, the definition holds automatically. Therefore, limit n tends to infinity n equal to c, where n equal to c for all n. If we consider equal to n, then there is no fixed real number L satisfies the definition of convergence. If we consider n equal to minus 1 to the power, the sequence oscillates between 1 and minus 1. So, no single real number L satisfies the definition of convergence. Similarly, if we consider n equal to sine of n, the sequence is bounded and no single real number L satisfies the definition of convergence. This is justified from the graphical representation of sine n. Now, we will prove that every convergence sequence is bounded. This theorem says that if n is a sequence and n tends to L as n tends to infinity, then n is bounded. To prove, let epsilon equal to 1, then for epsilon is equal to 1, there exists n1 such that mod of xn minus L less than 1. Thus, mod of xn less than equal to 1 plus mod of L for all n greater than equal to n1. If we take m equal to maximum of mod of x1, mod of x2, mod of x n1 minus 1, mod of L plus 1, then mod of xn less than equal to m for all n. So, the sequence is bounded. This theorem tells that unbounded sequences cannot be converged. And there are bounded sequences which are not convergent. Now, we will discuss algebra of convergent sequence. When two sequences are added, they are added term-wise. Therefore, if Cn is a sequence and Cn is equal to n plus Bn, then Cn, nth term of Cn is equal to nth term of n plus nth term of Bn. And if limit n equal to a and limit Bn equal to b, then limit of n plus Bn equal to a plus b. Therefore, limit of their sum is equal to sum of their limits. Similarly, for the other arithmetic operation. Now we'll discuss an important theorem, Sandwich theorem. This theorem tells that if a and bn are convergent sequence and n less than equal to cn less than equal to bn with a limit n equal to limit bn is equal to L, then limit Cn equal to L. Alternatively, we can state that if n is less than Cn less than Bn for all n greater than equal to k and limit n equal to limit Bn is equal to L, then limit Cn is equal to L. Proof. For proof, let epsilon greater than 0. Then for epsilon greater than 0, there exists n1 such that mod of n minus n less than epsilon for all n greater than equal to n1. Since limit Cn equal to L, then for same epsilon greater than 0, there exists n2 such that mod of Cn minus n less than epsilon for all n greater than equal to n2. Now we take n3 equal to maximum n1 and then put this inequality hold. Then combining this inequality, L minus epsilon less than n less than equal to bn less than equal to cn less than L plus epsilon. Thus, for n greater than equal to n3, mod of bn minus L less than epsilon. So limit n tends to infinity, bn equal to L. Now we will discuss an important sequence, monotone sequence. A sequence is said to monotone increasing if n plus 1 greater than equal to n, and a sequence an is said to monotone decreasing if an plus 1 less than equal to n. Monotone convergence theorem is an extremely important theorem. It says that if a sequence is monotone and bounded, it is convergent. This is one of the most fundamental result in real analysis. This is important because it allows us to establish convergence without computing the limit. More specifically, every monotone increasing sequence which is bounded above is convergent. Every monotone decreasing sequence which is bounded below is convergent. The idea of proof is as follows: if n is bounded and increasing, then supremum of n exists. Let L be the supremum. We can show that n tends to L using epsilon argument. Proof. Since xn be increasing and bounded above, so supremum of xn n belongs to n exists, and let L be the supremum. We'll show that xn tends to L. Let epsilon greater than 0. Since L minus epsilon less than L, so L minus epsilon is not an upper bound. Therefore, for epsilon greater than 0, there exists n1 such that xn1 greater than L minus epsilon. Because the sequence is increasing, xn greater than equal to xn n1 greater than L minus epsilon for all n greater than equal to n1. Also xn less than equal to L, since L is an upper bound. Thus, mod of xn minus L less than epsilon. Hence, xn tends to L. Let us take an example: xn equal to n by n plus 1. This is an increasing sequence and bounded by 1, and 1 is the least upper bound. So limit of xn equal to L. This is an interesting example. Here we see that xn is positive and xn plus 1 less than xn, that is xn is a decreasing sequence, and xn is greater than root 2, sequence is decreasing and bounded below by root 2, hence it converges. Hence it is a convergent sequence. Let L be the limit. By taking limit on both sides of the recurrence relation, we have L equal to L plus 2 by L by 2. Therefore, L equal to root 2. These are the conclusion and these are the references. This is our presentation for real sequences. For details, you must visit the study material stored in e-learning module. Thank you all.